Protective relaying is an integral part of any electrical power system. The fundamental objective of system protection is to quickly isolate a problem so that the unaffected portions of a system can continue to function. Protective relays are the decision-making devices in the protection scheme. These relays underwent, through more than a century, important changes in their functionalities and technologies. Each change brings with it odds and improvement in both technical and financial aspects. Power systems are susceptible to a large number of undesired events including lightning strikes, aircraft and motor vehicle encroachment, animal encroachment, icy and windstorms, switching errors, power surges. If any of these events occur, the power system can be damaged and customer service disrupted. Since the early days of the onset of electrical power, the need of devices to prevent or limit the undesirable events in power system have been prescribed. The history of protective relays refers to more than a century ago. Some literatures say that the first protective relay was produced in 1902, others refer to 1905. But whatever the date, the hard fact is that protective relays knew an important revolution since the beginning of the 20th century. In 1909, induction disk-type inverse time current relays came into practice and the concept of directional discrimination of faults was incorporated in these protective relays. Differential relay was developed using pilot wires for conveying information from one end to the other end of the line. In 1923, distance relay appeared in the form of impedance. Later, the induction-type mole relays with very high precision came into practice. After that, polarized DC relays with better accuracy and sensitivity were developed in 1939. All of the relays developed until the 1940s were electromechanical relays. These devices achieved very high precision and sensitivity in the form of induction cup mole relays and perform well for the missions attributed to them. The early 1940s showed the way into the development of relays using electronic devices. These relays are known as static relays or solid-state relays because they didn't contain moving parts. The advent of transistor circuits opened the door to the development of several new protection concepts like block spike comparator, phase comparator, etc. The major advantage of these relays was that no moving parts were needed for performing their intended functions. The operating speeds of these relays were also more than the speed of their electromechanical counterparts and their reset times were less than the reset times of electromechanical protective relays. In addition to these benefits, the solid-state relays could be set more precisely. This generation of static relays became quickly very popular and found a large place in power system protection. The use of digital computers and microprocessors for protective relaying purposes has been engaging the attention of research since the late 1960s. The first serious proposals for using digital computers came from Rockefeller in 1969. Much literature reported digital relays shortly afterwards. But the first microprocessor-based relays offered as commercial devices was only in 1979. In that era, the efforts were concentrated to obtain a very high-speed fault clearance. Different techniques and algorithms were proposed for achieving this objective. These include common hardware platforms, configuring the software to perform different functions. In the late 1980s, multifunction digital relays were introduced to the market. In 1988, the Virginia Tech research team developed the first prototype phasor measurement unit PMU-based relay. This technique allows measuring, beside the magnitudes of the electrical entities, the phase angles and could offer new information that can be used to improve the functional logic of protective relays. In the 1990s, the notion of integrated protection and control became very popular and benefited full advantage of microprocessor technology for protection, monitoring, control, disturbance and event handling, and communication. The relay's volumes as well as wiring were significantly reduced due to the integration of functions and the use of serial communication. It is the job of power system protective equipment to detect the onset of undesired events and take appropriate action. Appropriate action often includes the tripping of circuit breakers. Circuit breaker tripping isolates the trouble from the remainder of the power system and minimizes damage. Relays can be broken down into a few major classifications: monitoring relays, such as high temperature or gas and oil relays, which monitor power system quantities and initiate an alarm if those quantities are outside of set limits. Auxiliary relays, such as timers, tripping, reclosing, or lockout relays, whose job is to supplement the actions of other relays. Programming relays, such as automatic synchronizers and generator auto-start relays, which go through a sequence of program steps to complete an operation. Regulating relays, such as a voltage regulator, which takes some action to keep a power system quantity within a desirable range. Protective relays, such as overcurrent, overvoltage, or distance relays, which protect the power system from damage. The purpose of protective relays is to minimize damage and isolate problems. System reliability should not be affected outside the immediate problem area. An important point to remember is that protective relays do not prevent trouble. Relays respond to trouble and minimize further damage. Relays cannot keep animals out of the buswork or lightning from striking a transmission line tower. Relays work quickly, usually in a few cycles, to isolate the source of trouble and avoid further damage. In the application of relays to the power system, it is desirable to have the relay operated as quickly as possible, so speed is one determining factor in relay selection. Of course, cost will also play a part in the selection. A related factor is complexity. Complex relay systems are difficult to work with and are costly to purchase. In judging relay performance, selectivity, sensitivity, and reliability all play a large role. Selectivity is the ability of the relay to isolate the smallest area of the power system in order to ensure that no further damage is done. The goal is to not disrupt more of the power system than is necessary. Sensitivity: it is vital that relays be able to detect all faults that jeopardize the power system. Relays must be set sensitive enough to accomplish this goal. However, if set too sensitively, a relay may initiate tripping for events which are not a threat to the system. Reliability takes into account most of the principles just described. A reliable protective relay system should operate when called upon with sensitivity and selectivity, yet should be secure against tripping when not necessary. Power system faults. In normal three-phase power system operation, electrical power is generated at the power plant and eventually supplied to the load. Current flows through the transmission and distribution system on one or more of the phase conductors. The current path is then closed via a ground path to the source, the generator, to form a complete circuit. When a path for current is established that is not desired, a short circuit, it is known as a fault on the power system. The closer the fault is to generators, which are the source of voltage on the power system, the greater the fault current can be. The fault current is larger because there is less impedance between the fault and the source, the generator. Fault current values in the tens of thousands of amps are common on the high voltage transmission system. The term short circuit means that an unusually low impedance current path has been formed. Typically, a short circuit involves bypassing the load impedance. Line to ground fault. The most common type of fault on the power system is a line to ground LG fault. One way of incurring a LG fault is illustrated in figure. The overwhelming majority of LG faults are caused by lightning either striking or inducing a large voltage on the line conductors. LG fault current magnitudes can range from barely noticeable up to values equal to three-phase faults. Equipment can be damaged due to the high current magnitudes. LG faults also create an imbalance in the power system. Balanced power systems have equal currents and voltages on all three phases. During LG faults, the imbalance may damage rotating equipment such as motors and generators. Line-to-line faults is the next most common fault on the power system. LL faults can be caused by something as simple as wind blowing two-phase conductors together as in figure. LL faults also cause an imbalance in the three-phase system. The imbalance impact on generators is the most severe with this fault type. Fault currents are typically high for LL faults. In addition, the ground may or may not be involved. If ground is involved, the fault is called a double line to ground fault. Three-phase faults where all three phases are involved are the least likely to occur. However, three-phase faults are usually the most severe as far as levels of fault current are concerned. One way of producing a three-phase fault would be energization of a transmission line with a three-phase ground switch still closed. Since three-phase faults are the least likely to occur and are usually of a permanent nature, a structure down or a ground switch closed, automatic reclosing is not permitted on the transmission system for this type of fault. Automatic reclosing is an automatic attempt to re-energize a transmission line following a short time delay after a transmission line trip. Instrument transformers reduce power system currents and voltages to lower values. These lower values, called secondary values, can then be input to protective relays, meters, and other devices. The power system voltage and current magnitudes must be reduced as they are simply too large to measure directly in any safe and economical manner. Instrument transformers may be classified into two basic groups: those that are designed to transform high currents, and those that are designed to transform high voltages. Current transformers. Instrument transformers designed for transforming current magnitudes are called current transformers, CTs. CTs produce a small secondary current flow, a few amps, that is proportional to a larger primary current flow in the power system. The schematic symbols for CTs are given in figure. Two symbols are illustrated. A bushing CT is located in the bushings of electrical equipment. The standard CT is a standalone device. Potential transformers. Instrument transformers designed for the purpose of transforming voltage are called potential transformers, PTs. Potential transformers are also commonly referred to as voltage transformers, VTs. PTs produce a small secondary voltage, perhaps 120 volt, that is proportional to the higher primary voltage in the power system. The schematic symbol for a potential transformer is given in figure. A variation on the PT concept is the capacitively coupled voltage transformer, or CCVT. A CCVT is a